Okay, so next we have Edoardo Orzes. So Edoardo joined CERN during his final year at the University of Pisa, where he graduated as electronic engineer focusing on wireless and RF technologies, and started his career here in the HPTD team, working on the digital electronics for high precision timing and investigation solutions to stabilize phase at the picosecond level. And during his studies of the AMD phase interpolator, he found some non-linearities that he is going to tell us about now. Please welcome Edoardo.
Thank you. Hello. So I will present the characterization of this phase shifter that AMD provides in their transceivers and the consequences on phase compensation systems. So I will start with the timing requirements for the high luminosity upgrade of the LHC, and then I'll show some methods to achieve phase stability. And then I will present this characterization of the nonlinearities of the phase interpolator and the consequences on phase stability, to then conclude with the proposed solutions. So let's start with the bunch structure of in the LHC. So particles are grouped in bunches with a size of 2.5 nanoseconds and spaced by 25 nanoseconds. And this structure is maintained stable thanks to the 400 megahertz radio frequency, which is generated at point 4 in the RF cavities. And these cavities also generate the 40 megahertz bunch clock, which is a clock phase locked to the beam, which gives the rhythm of collisions of particles. And this bunch clock needs to be distributed to the thousands of endpoints in the experiments for data retrieval. And so with this high luminosity upgrade, there will be at least 130 collisions per bunch crossing, all occurring in a time window of 325 picoseconds. And so there will be superposed collisions, and this effect is called the high pileup. And so to disentangle the superposed collisions that all occur in the same point in space, it will be needed the time dimension. And so new timing detectors are being installed for this purpose. So for example, the high granularity timing detector will reach a timing resolution of 30 picoseconds, but this will demand phase stability for the entire timing distribution system of less than 10 picoseconds RMS. So we see here an example of a timing distribution tree. So this is composed by a cascade of boards transmitting a serial stream to the thousands of endpoints in the detectors. And each board hosts an FPGA that performs a clock recovery on the serial stream, and the recovered bunch clock is used as a reference clock for the following transmission of the cascade. And so in the serial stream is basically embedded the bunch clock. So this way, in each node of the cascade, there is a fixed latency between the transmitted data and the received data, so that all the endpoints in the detector will receive a bunch clock which has a fixed phase relation to the original bunch clock from the RF cavities. And here we see a few examples of state-of-the-art solutions to achieve phase stability in such a system. For example, we have the TC-Link, which monitors the round loop phase variations in fiber between the downlink and the uplink fibers. And then it applies a phase shift from the transmitter of the master FPGA to compensate for the measured drift. And another technique is the TX phase aligner, which at startup aligns the phase of the transmitted data to the reference clock of the transceiver. And so both of those techniques rely on the AMD phase interpolator to perform the phase shifting. And this phase shifter has a nominal step of 1.6 picoseconds across different line rates. And so now I show the characterization of this phase shifter to see what is the actual step size. So in this test bench, I place an FPGA in the climate chamber at constant temperature, and I phase shift the data, and I send this data stream to an oscilloscope, and the reference for the transmitter is provided by a free-running reference PLL. So the oscilloscope performs phase measurements between the transmitted data stream and the reference clock. And to do the phase measurement, I transmit a clock pattern on the data stream, which is a sequence of 0 and 1s to resemble the reference clock frequency. So this phase interpolator has 128 steps. This is the range. And so I phase shift by 1 step at each measurement. So I do 128 measurements. Then I repeat this process 4 times. I average the 4 batches that I get. And then I perform, I subtract from the ramp that I obtain the ramp of nominal steps. And so basically I obtain the integrated non-linearity. And from this, I do a Gaussian process regression to extract the underlying feature from the noisy measurements. And so this is what I obtained. So we have, for each of the 128 steps, I have the value of the error. So I repeat this process for many transceivers. So we see 3 different types. We have the Virtex GTY4, the Zinc GTH4, and the Versal Prime GTY5. And we see different effects for each transceiver. And for each transceiver type, I tested 2 transceivers of the same type. And we see variations ranging from 1 to 5 picoseconds. And here you can see a processing of these measurements where I basically represent the differential non-linearity, and I express it as a difference from the ideal step instead of as a ratio. So this is interesting in a phase compensation system because we see basically what is the error that we introduce when we shift by 1 step. And so we see errors ranging from half a picoseconds for the Virtex and Zinc and up to 1.4 picoseconds for the Versal Prime, which is close to the step size of 1.6 picoseconds. And then here we see some processing that I will leave here for later. And this is basically the difference between the error from one UI to the next UI in the range of 2 UIs of the phase interpolator. And one UI is the serial bit time. And the range of the phase interpolator, I repeat, is 2 UIs, so 1 serial clock time period. And so the conclusion from this characterization is that basically all tested transceivers present different non-linearities. So the non-linearity is an analog feature that depends on the silicon, and so it's not a digital feature of the transceiver. This non-linearity is not temperature dependent, and this has been verified. And then it's interesting to observe that all tested transceivers present different non-linearities, but the underlying feature is the same, and it is a 4-period sine wave. And this is explained by the architecture of the TXPI, which basically performs a weighted sum of the currents of 4 clocks. And those clocks are 2 couples of in-phase in quadrature clocks, where basically each clock has a phase relation of 90 degrees to the other. And so this explains this trend of 4 periods sine wave. Is basically the combination of those 4 clocks. So the consequences on a phase compensation system is that at each iteration, there is basically one phase measurement and one phase shift, and the phase shift will introduce the error due to the nonlinearity. And so this will either introduce a jitter or wander based on the speed of the loop. So the solution I propose is not to characterize each transceiver individually, because that would be not feasible, but instead to define an ideal trend for the error, which is an ideal sine wave with a fixed amplitude, for example, of 1 to 1.5 picoseconds, and then to use this prediction of the error to do a smart adjustment decision. So here we see a test bench to demonstrate this technique. So basically, we have the same setup of before with an FPGA at constant temperature in a climate chamber with a reference clock from a free-running PLL. And this transceiver is sending data to the oscilloscope, which measures phase of the data relative to the reference clock. So the loop, the testing loop is very simple. First, you measure the data between the first you measure the phase between the data stream and the reference clock, and then you apply a phase shift to reach the target phase. And in this case, the target phase is not a constant phase as it will be for a phase compensation system, but it is a ramp. So the goal here is to have the phase of the data following this ramp. So the algorithm that I propose is based on 3 steps. First, you define the shift that is required in picoseconds, which is the difference from the measurement to the target phase. Then you define the delay that you need on the phase interpolator. And this is the current position of the phase interpolator times the step size in picoseconds, plus the error that you have at that step position, plus the shift you need to reach the target phase. And so the step that you actually need on the phase interpolator is given by a function that minimizes the error of this required delay, where the error is given by this ideal sine wave that has been previously defined. And so this is the result. So we see an histogram representing how close the phase gets to the target. So on the left, you see, without considering the error, we have 0.8 picoseconds RMS and 5 picoseconds peak-to-peak, while if we consider the error, we have an improvement of 2 picoseconds peak-to-peak. And then I conclude with this other application where basically the TX phase aligner is using the phase interpolator to perform an adjustment of the transmitted data stream at startup of the transceiver. So the issue here is that, so basically, this TX phase aligner, what it does is to align the transmitted data to the reference clock after a reset. And to do so, it uses the TX phase interpolator to shift the serial clock and the parallel clock in the transceiver until the phase of the parallel clock is fixed latency to the reference clock. And this condition is achieved when the elastic buffer, which is a FIFO in the transceiver, is half-filled. And so the reason for which there are phase jumps at startup is that the reference clock is fed into a PLL, which generates a serial clock. And then the serial clock is divided back to the reference clock frequency. So this divider is not deterministic among resets. And the number of possible phases that the data will have is given by the ratio between the serial clock and the parallel clock. And so the possible phases of the data relative to the reference clock is quantized. And so the phase interpolator at startup will shift by a multiple of the serial bit time of the UI. So maybe you can already imagine the problem. So is that the distribution of the transmitted data phase will have a double peak distribution. And this is because the difference between the errors among 2 adjacent UIs in the TXPI characteristic, in the phase interpolator characteristic, this difference between UIs, between the errors on 2 adjacent UIs, is exactly the double peak spacing. So when you reset, you will shift by a certain number of UIs, and you will have a certain error. You reset again, and you might end up in the UI next to it, And so the error will be different because the range of the phase interpolator is 2 UIs. So the difference between the errors maps exactly this double peak distribution that you get in the transmitted data phase. And so you can see this one-to-one correlation between the accumulated phase in the phase interpolator and the double peak spacing of the transmitted data phase. And so we see here an example of 1.1 picoseconds of spacing in one transceiver and 1.7 in the other transceiver. And this is the measurement from before. So here we see the difference between the error in one UI to the other UI. And this is from the characterization of each transceiver. And this is a way to map the space of all possible double peak spacings that one can get with a certain firmware. And it's interesting to observe that the position on this map, so basically the size of this double peak spacing, entirely depends on the phase relation between the divided parallel clock and the reference clock. And this phase relation depends on the routing, meaning that when you recompile the firmware, you will get a different routing length. And so you will land on a different position in this map. So you will have a different double peak spacing. For example, we see in the Versal Prime GTY5 that for 50% of the time, you might end up with a delay that doesn't cause any double peak distribution. So the two peaks are basically 1. And for the other 50% of the firmwares, you will end up with a double peak spacing up to 1.6 picoseconds. And so the solution that I propose is very simple, is to log the accumulated phase at the startup in the TIX interpolator, the TIX phase interpolator. And if this phase is less than 1 UI, so less than 64, you keep it. If it's larger, you do a reset, and you check again. So sort of a roulette approach until the TIX phase aligner lands in the same UI all the time, so it has the same error, and so there is no double peak distribution. And so to conclude, the high luminosity upgrade demands phase stability less than 10 picoseconds RMS for the entire timing distribution system. And there are novel techniques that are relying on this phase interpolator to achieve phase stability. But this phase interpolator suffers from non-linearities that degrade the compensation systems. And so, for example, we have seen that in the TC-Link that is responsible for compensating for temperature-induced phase variations in the fiber. With this system, we can use a smart basically step decision based on a prediction of the error given by this ideal sine wave. And we improve by 2 picoseconds peak to peak by performing this operation. While for the TIX phase aligner, this brings startup determinism in the transmitter. And this as well can be improved by 2 picoseconds peak to peak by doing this roulette approach based on logging the accumulated step of the phase interpolator. And that's all. Thank you.
Thank you, Edoardo. So any questions? Yes, go ahead.
Hi, and thanks for the great talk. So I was just wondering, how do you do your phase measurements? Do you just put everything on the scope and then you average for these 6 hours that you can see in your diagram, or what do you do?
Yeah, so the phase measurement is done by letting the scope running for 10 seconds and accumulating measurements. The time interval is 100 microseconds, and the total count of measurements that I average is 300,000 in this time interval. And then I repeat the measurement 4 times, and I average again. So it's a lot of averaging, and then I also do the Gaussian process regression to eliminate all the noise. So it looks very clean because of all this processing. So it's not feasible to do this for every transceiver. Every transceiver is different, so it makes sense to use this ideal sine wave, which is similar to the actual feature. Thank you.
Thank you. So, go ahead. Yeah.
Sorry, I thought you were looking somewhere.
Was I looking too high?
But if you, how stable is such a measurement in the sense that you do it as you described? And so my curiosity is, if you do it over many transceivers on the same FPGA, how much does it change? Do you need to do it individually? And also, if you repeat it after a week or after a month, does it change?
You're talking about the characterization, the real characterization?
Yeah,
Yeah.
these curves that you...
So I tested, so let's see. So here I tested different transceivers. You see there are quite some differences, but this is very stable. So each transceiver has that trend, and that doesn't change. You can see in this one, I repeated the 128 steps of range 4 times, and all the time is exactly the same. And I also tried to change temperature in the FPGA to see if this trend changes, but it doesn't change with temperature.
But when you say each transceiver, like in the titles of your plots, I see you say GTY E5 for the Versal Prime, for example. Is that one specific?
Yes.
So another one could have a different curve? Or?
It does. You see here, there are, for example, for the Virtex GTY4, there are, I'm showing 2 transceivers. Those are 2 different transceivers, the same transceiver type, but 2
okay, in the column there are 2 of those, and in fact they are different.
Yes, yes. It can be quite different because it really depends on the silicon. So, yeah.
So you do it individually for each?
Yes.
Okay.
And of course, the solution that I propose is not to characterize each, because that would be impossible, but to use this ideal sine wave, hoping that it matches the real feature of the transceiver.
But do you have some deep understanding of why it's happening like this? So
deep, it depends, but the explanation I have, and this is my guessing because there is no documentation of this, so the explanation is that this explanation is based on the receiver, because the receiver is a bit more documented, and it shows that it uses 4 clocks, which are 2 pairs of clocks in quadrature, in phasing quadrature clocks, with a 90-degree difference one to the other. So you see 4 oscillations, which to me it's quite evident that this is the combination, the linear combination of those 4 clocks, and this oscillation you see is the non-linearity of the linear combination. It is not perfect due to the silicon imperfections.
Thank you.
More questions? Yes, go ahead.
Thanks for the talk. Very nice work. I wanted to ask, so on the slide where you showed the error, I noticed the error was in picoseconds. What is it relative to the nominal, like as a percent?
Yeah.
It depends on, you're running at like 10 gigabit, so you're expecting something like 0.9 picoseconds per step. So it looks like it's nonlinear and it's non-monotonic. It's actually worse than the nominal stack at some points. Is that true?
Yeah, so the step size is 1.6 picoseconds across different line rates. So if you change the speed, you will still have 1.6 picoseconds. I tried at different speeds, and it's true, because the dividers and parts of the transceiver are adjusted to have the smallest possible step. I remember that for one specific frequency that I don't remember, the step is even smaller, is 1.2 picoseconds, but it's always around that range. And so here I express in picoseconds to show the actual error in picosecond, basically. And we see it's ranging from 0.5 picoseconds, which is significant compared to the step size. But in the Versal Prime, it's, you can have an incremental error between adjacent steps of 1.4. The nominal step is 1.6, so it's almost a step of error.
Oh, so if it seems like on all of these charts, it never goes higher than 1.6, so maybe it's monotonic still, so it's nonlinear, but you never have a step backwards in the wrong direction.
Yes, exactly.
So I saw another plot where it looked like it exceeded, maybe it was measuring something else, but
No, I don't show it, but it might happen because I tested 2 transceivers per board. There are hundreds, so maybe in some it exceeds, but that's difficult to say.
I guess that's just more important for, the TC link for the control.
Yeah.
You want to make sure. Thank you.
Yes, thank you.
Okay, go ahead, next question.
Yeah, thanks for the very interesting talk. Correct me if I'm wrong, but I've understood it the way that you're using a sine wave to estimate, or like to
Yes.
have an estimate for the non-linearity. Have you experimented with a higher order sine wave function, so with like a Fourier series of a
Yes.
certain order, or like as to why that may or may not be a good idea?
Yes, I performed a Fourier analysis of all those curves, and there is this. Yes, there is this feature of the 4-period sine wave. For the versal prime, you see more. It's more nonlinear. So the frequency, I will say, I remember there are 8 period, not 4, for the versal prime, but it's still, if you look at the feature by eye, you still see these 4 oscillations within. So you have both 4 or 8 as a frequency. But maybe I missed your question. I didn't hear perfectly. So did I reply or not?
I couldn't fully understand you acoustically, so I can't say if you replied, actually. But yeah, the question was just if it would make sense to use like a Fourier series to a certain order for as the estimate for the nonlinearity instead of like just one single sine wave.
Yes, the problem is that you don't know what is the real feature. So this choice of 4 periods, sine wave, is the one that better matches all the possible results. So to do a better decision, you would have to characterize the transceiver, but then if you characterize, just use the characterization. So thank you.
Okay, more questions? No more questions. Okay, then let's thank the speaker again.